Good evening, everyone. You're watching Science on Reaction, live, interactive, international science stream. Thank you, everyone, for joining us today. My name is Oliver, and I'll be your host. Let me start by telling you a little bit about us. Science On is a science communication and networking platform. We stream in Czech language every month, and every 6 months we are holding an international stream. We love experimenting. We love science experiments. We try them, we film them, and we are always excited about the results. And not only if the experiment actually did go well, but also what kind of reaction did it provoke. And today's all about that. We will see some action, most probably some equal and opposite reaction, and hopefully a lot of interaction. And most importantly, we will see 6 great performers having their take on today's theme. And we're super excited about today's lineup. We have 2 teachers from the Netherlands, we have a science communicator from Switzerland, and we have 2 science enthusiasts from Czech Republic joining us live. On top of that, we have a very special treat for you tonight. We received a video, literally from the other side of Earth, by our dear friend Stuart, Science Nomad. He shot a video exclusively for Science On and exclusively for this upcoming holiday season. So you don't want to miss that, and we are really excited to show you that later tonight. So stay tuned. We are streaming to Twitch, YouTube, both our channels, to Facebook and Instagram. And before we start, let me also thank a grammar school, Mirovo náměstí in Brno, for their kind support and the possibility to stream on their premises. And now, without further ado, let me officially start reaction. I would like to introduce our tonight's guests. First, joining us from their chemistry classroom at their school, Stellingwerf College from Oosterwolde in northern Netherlands, it's Mark Bette and Sarina Maar. Welcome, Mark and Sarina.
Hello.
How are you doing today?
Good. Thank you very much. A little bit nervous.
Perfect. Yeah, I think it goes with it. Thank you very much for joining us, and I would like to start. Sarina, what can we expect from your experiment today?
Well, I have an experiment about really nice red nail polish, because I like nail polish and I like to do my nails. So that I interacted in an experiment. Perfect,
thank you. And Mark, what about you?
I want to make a gel fuse, and we make that with eggshells.
Wow, okay, perfect. Thank you very much both. We're looking forward to see you later.
Thank you.
Thank you.
Next, born in Slovenia, but now joining us from CERN, Switzerland, it's Anja Krajnc-Horvat.
Hi. That was
Hi,
a lovely
Anja.
pronunciation of my last name.
Thank you very much. I tried like 100 times before the stream. So Anja, what can we expect from you today?
Well, I will just continue the conversation that the previous performers have started, and I will show you why it's sometimes cool not to polish your nails.
Oh, okay. So kind of reaction to the first action. Perfect.
Exactly.
Thank you very much. We're looking forward to seeing you later. And in our studio, I have with me Adam Blahák.
Hi.
And David Číhal.
Hey.
And let me start with David. What can we expect from you today?
I'll need help with solving a really basic but mostly fatal problem which every other scientist solves in a laboratory if they don't make their notes correctly.
Okay, so note taking. Perfect. And Adam?
We're gonna look at nuclear reactions more closely, which are occurring inside a nuclear reactor in power plants.
Oh, perfect. Thank you both. And I think we can start with the presentations. Before we actually start with the performance of our first performer, I would like to speak to our dear audience. As I mentioned just at the start, this is an interactive stream. And to make it interactive, we need your help. So it's mostly up to you how you will be interacting with our performers. But they will be asking some questions. Don't worry, don't hesitate to answer in any way you can. You can use any platform that we are streaming on, so it can be comments under the YouTube video or in the Twitch discussion or comment section or any other platform. And don't hesitate to use any kind of simple English. We are not testing you. We want to engage with you. I will skip to Czech or Slovak language for a little bit. Pre všetkých našich českých a slovenských divákov tak chceme povedať, že môžete určite dávať komenty aj v slovenskom alebo českom jazyku a my si tu ich v tomto anglickom streame preložíme. Naspäť do angličtiny. And back to English. And we will start with the first performer and it will be our own Adam here in the studio. So, welcome, Adam.
Hello again.
And if anyone was following more than one stream with you, then everyone knows that you are very, very passionate about radioactivity.
Yeah, that's true. That's true. That's my topic.
Yeah, and you take your Geiger-Miller counter everywhere you go.
That's true. That's true.
Yeah, also in the places that maybe it's not at all, or it's not fully legal. Is that correct? No, don't admit that. As once a wise man said, don't incriminate yourself on live television. It's a good advice.
All right. But I think I was only on legal places.
Okay, great, perfect.
Yes.
And so I wanted to ask you, my question is, have you ever experienced regarding to radioactivity, a situation that provoked a very strong, unusual, and unexpected reaction in you? So, for example, if you ever measured something so bizarre that you just dropped everything.
Not sure. But last time when I was in Science Center in Liberec, Landia, there was one place where was higher amount of radioactivity background, and then I discovered that behind the wall there is some samples of uranium and americium and others. Okay. So it was kind of strange to find that your Geiger counter just start beeping around and on the places which is public, basically.
Okay, so according to the advice of not incriminating, I will not ask you if you did steal something.
I didn't, but I tell them that I measure it. So.
Okay, perfect. Okay, so about the radioactivity, and I wanted also to ask you about your upcoming, what is it, training or a test for radioactivity safety.
Yes, that's true.
So can you tell us a little bit more about it?
Because when you want to work with some radioactive samples, officially you need some permission of government, and you must take some course and test after it.
So just catching up on bureaucracy.
Yeah.
Okay, that's perfect. So now the stage is yours.
All right.
I'll leave it up to you, and we are really looking forward for what you have for us.
Okay. So let's start. Hi again. And now we're going to talk about nuclear reactions. So we're going to type it down. Here are our nuclear reaction, the NR. Lovely. And we're going to focus more on nuclear reactions inside a nuclear power plant. So, yeah, this is our nuclear power plant in Czech Republic called Dukovany. It's near to Brno, where I live. And especially we're going to look on one place, which is called nuclear reactor, as you can know, and how, as we can tell, that there are the most reaction occurring just there in nuclear reactor. So we're going to focus on this place, but I want to also ask you about questions on where can we meet another nuclear reactions. So where are the other places where we can find a nuclear reaction, except this one in nuclear power plant, the nuclear reactor? So this is the question. So we can show it. Yeah, here is our question. Yeah, and start with our nuclear power plant, the nuclear reactor. For our nuclear reaction in power plant, we need some fuel. Yeah, you know, maybe you know that the fuel is our famous uranium. So this is the stuff. This is uranium, nature occurring uranium. So if we put Geiger counter near to this sample, yeah, it's kind of radioactive a little bit here. So this black stuff, it's a uranium oxide, which is used for the fuel. But we must process it a little bit to enrich this, because the most uranium inside this sample is uranium-238. But we need more of the second most common uranium, uranium-235. And this number means if we have uranium-235, this number means how many protons and neutrons are inside the nucleus. So this is, for example, this is our model of uranium-235. So there are 235 particles. These green ones are neutrons, and these orange ones, or what color it is, orangish ones, are protons. And the number of protons is often written in down corner on the left. So it's 92 protons. This is our uranium, which is used for to not create, but to have some energy, to make some electric energy or thermal energy, and then electric energy in an electric power plant, nuclear power plant. So we're going to try to make a fission, which is the most famous nuclear reaction, which is occurring inside the nuclear reactor. So we need our fuel, and also we need a neutron. So these greenish balls will be our neutrons. This green one, or this hairy greenish ball here. So now we're going to try to hit our nucleus of uranium and to make it fission, to destroy it a little bit. But we must hit it first with our nucleus. Yeah, but our neutrons are too fast, so we need to make it slower to aim better, basically. And for that, in nuclear power plants, the water is used, because water is basically 2 hydrogen, so this is our hydrogen. A hydrogen is 1 proton, or 1 proton and 1 neutron, it also could be. And when the neutron hit our hydrogen nucleus, it slowed down the moving neutron. It comes back, it shouldn't happen, but it happened. So this slows down our neutron and it could hit our uranium. Now it happens. And the uranium core, the uranium will just destroy it. This is called the fission. And after this reaction, the 2 or 3 or sometimes 1 new neutrons just start moving around from this fission reaction. And also 2 new elements, 2 new isotopes of some elements are creating also. And thanks to the neutrons which are leaving our atom, we can continue this process again, and this takes us to another model on our floor. So here it is. This is, need to aim a little bit, and we need the light maybe. Yeah, so, but I can describe what it is. This is our model of chain reaction. This is uranium, and this is the we're gonna, yeah, thanks for the light of my life maybe. So this is the line where the neutron, which will travel to our near to our uranium nucleus. So we try our nuclear reaction a little bit, and we can see that there will be more and more fission reactions with neutron and also with uranium. And with this reaction, the energy is created. And if we don't control it like this, as we see, the principle of nuclear weapon will be there. So this is something what we don't need. We don't need that much energy. We need to increase the creating energy. So we need some element or something to catch the neutrons. And we use the control rods, which are created from material boron. This is a nucleus of boron. And if we just if the boron meets our neutron, it will catch it, and then the neutron can't make the reaction with the uranium. Yeah, here it is. Sorry. Here it is. Boron. So this is it. So we can put to our model of chain reaction a little absorbator, which is the boron, and now we can see that the reaction is more controlled. It's not that wild. Yeah. So this is something what we need. So let's go to the board, because we can describe it with a little bit of equations, which is a lovely thing in physics. And these were the reactions with neutrons, which is one neutron and one neutron and protons and 0 protons, basically. And we see the fission reaction, fission. There are 2 S, I think. I'm not sure. Fission, yeah, 2 S. Fission reaction, which is creating that we smashed our uranium atom, the uranium nucleus, to 2 pieces. And there, if we write it down, there will be uranium plus neutron, and it leads us to krypton and barium and some number of neutrons, for example 3, 2 or 1 neutron. So we can put it right this in these equations. And if we write down the atomic and nuclear numbers, we can have it like this: 235 and 92 and 10. And if we add it up, all the numbers, it should match, I hope. So this is our fission reaction, but the products of this fission reaction could be different also, because we don't know how we just smash the nucleus. So basically almost everything lower than uranium could be created theoretically, but everything is about probability when some elements are created. And also we got the capture with the boron, capture reaction, which means there was a boron with 10 protons and neutrons, and we just hit it with neutron, and it led us to boron 11, which is also stable, and some remains energy just vanished with some gamma rays. And there was also the scattering, which means that the scattering reaction, the nucleus scattering reaction, which was occurring when we slow down our neutrons. So this was also the reaction. So these reactions are the basic principle of nuclear reaction inside, or nuclear reactions inside the nuclear power plant, inside the nuclear reactor, inside of it. So this is the basics. And now let's look at the answers. Yes, I forgot almost. Yeah. This is the amazing schematics picture of nuclear reactor. The fuel rods. In fuel rods, the fission reaction is taking place. In a moderator, which is mostly water, the scattering reaction is there. And inside the controlling rods, the capture, neutron capture is there. We can find it right there. So, and where we can find another reactions, nuclear reactions. What did you write? Are there any answers? Yeah, we can observe nuclear reaction in atmosphere in my option. Yeah, that's true, that's true. The nuclear reactions in atmosphere is important, for example, for carbon dating, because in this reaction the carbon-14 is created. So this is interesting and important. And do we have another? We don't have another reaction, so it doesn't matter. If we are talking about energetic field, another nuclear reaction is important, a lot of important, and is a fusion reaction. So fusion. Are there 2 S? No, there is only 1 S, sorry. So fusion reaction. And it means that we don't break atoms, we don't break a nucleus, we combine them. So we got one hydrogen, the heavy hydrogen, super heavy hydrogen, and the hydrogen, the heavy hydrogen, and it will fuse together, and another energy is created. and the one neutron will leave this reaction. So this is maybe the future of energetic, and this maybe will be a future way to make some electric energy. Nowadays, this fusion reaction is occurring in the sun, and this is where our sun makes energy, or have energy. And we can end this performance with a little bit reaction, not nuclear reaction, not a real nuclear reaction, but with chemical reaction with hydrogen. Because for demonstration how much energy is in hydrogen, we can use it for chemical reaction. In this balloon there is a hydrogen, and we can start this reaction with a little bit of fire. So embrace yourselves, take your earplugs or anything, and this is gonna be loud. Yeah. So prepare for everything. So 3, or we can make it a little bit lower maybe. Ah, it's all right. So 3, 2, 1.
So thank you, Adam.
Yeah, you're welcome.
Thank you for the whole explanation, very visual, very tactile, I love it. And also explosive ending.
Yeah.
And I would like to ask you about the beginning of your experiment. You were showing how you were trying to aim at the uranium with neutrons, and you told us that it's you have to slow them down to aim better. So what is the connection there? How exactly does slowing them down help aim better at the uranium?
Yeah, this is a good question, which I also have, and I'm more of the nature radioactivity than nuclear reactions. I'm not a nuclear physicist. I'm more of the radiation itself, which is nature occurring. So I'm not on this artificial one, and I'm not really sure. I maybe could describe it in Czech, but in English I'm a little bit on the edge. So.
Okay, so if everyone is also interested, I encourage you to ask the question in our comment sections, and Adam will get to them later after the stream. Right? Thank you very much, Adam. I think we are ready to continue with our next presentation. And it's time to welcome Mark back on stage. Welcome, Mark.
Hello.
So, Mark, we know that you are a very passionate chemistry teacher, and I can imagine that also a very popular one. And I would like to ask you, during your lectures, is there any kind of theory or experiments that you would like your students to be more excited about than they are now, and you find it challenging to engage them with or in?
Whoa, that's a very difficult question, because we have a lot of very nice experiments. And the fun thing is we make the experiments really for our students. It's not for me only to use chemistry and experiments for explaining the theory, but to engage the children also. So last week I had a lesson where I used magical money. It's fake money that burns very fast, and when you throw it in the air, there are no leftovers. And when you look at the faces of their children, they're so happy to see that. Then I'm happy.
Okay, thank you. Thank you very much. And also I would like to show a little clip that we have for our audience.
Sorry? Yeah, that's me also.
Yeah, that was not a question, that was just an introduction to the question. So,
didn't expect this.
Yeah, it was judo practice or maybe a judo event. And yeah, we wanted to ask you, we know that this is your hobby and you're very passionate about it. You compete and you also judge, you're a referee for the judo tournament. And let me just do a quick connection. If you hear judo and reaction, what is the first thing that comes up to your mind?
That judo is all about reaction, because if my opponent attacks me, I have to react. And sometimes I fake an attack so that my opponent will react, and then I can continue with another technique. So the whole thing about judo is reaction, action and reaction.
Perfect. So tactics about opponent's reaction to your action. Perfect. Exactly. Thank you very much. And so we are very happy to have you today and so excited to see what you have prepared for us. So the stage is yours.
Okay, thank you very much. Thank you. So, thank you very much for having us here in this fantastic event. Before I start, I want to give the organizers a very big compliment, because they already organized this for 2 years or so, and it's a high level for all the teachers in all the world. So I think they need a big applause. So. And after applause, and I am sure that all over the world people will give their applause, I will start with my presentation. So my colleague Sarina, who will have a performance later on this evening, are very interested in very small and simple experiments, because that illustrate, and then we can illustrate a lot of chemistry during that experiment. So today I have a very small experiment with me, and this experiment is done by children in the age of 14 to 15 years old at our school. And after they have done this experiment, they will have to write a lab journal or a practical report. So the context about this experiment is, when you go to a restaurant, you sometimes see this, because the restaurant has a buffet. And the buffet has au bain-marie, things like this, to keep the dinner warm for a very long time. So the water is heated by gel burners like this one, and to make a gel burner you need a gel, of course, and you need something that's burnable, flammable. In this case alcohol is used, and to make the gel you need a material like calcium acetate. And we thought that it would be very nice if we could if our students could make the flammable gel with chemicals that we have in our home, in our kitchen. So since we have Corona, all the households probably have alcohol, so that won't be the problem. But the other thing is, we have to make calcium acetate, and to make calcium acetate we need to have calcium carbonate and vinegar. So vinegar is not a problem, because we used it normally in salads or other reasons. But how do we get the materials to make calcium carbonate? So we use eggshells for calcium carbonate, because the main ingredient of the eggshells is calcium carbonate. So our students and we collected eggshells and grinded them, powdered them, crushed them till a powder, and this is the powder. And for this experiment we use approximately 2 grams of calcium of eggshells. So here we have 2 grams of the eggshells, and then we pour 10 milliliters of acetic acid vinegar to it. So, and we will switch to the small camera so you can see some details. So you can see that a foam is forming, and this indicates that the reaction has started. In the Netherlands we have 2 types of vinegar, 4% acetic acid which you use for salads, and 10% acetic acid, which you use to remove weeds. So at this point, I have used the 10% mixture because the reaction then goes faster. So now the calcium carbonate from the eggshells react with the acetic acid, and this produces calcium acetate and carbon dioxide, and the carbon dioxide forms the foam. So you can see now that the foam formation has stopped, and this indicates that the reaction has stopped. So this means that one of the starting materials has completely reacted. So thank you. You can switch to the big screen now again. Thank you. So now we have a mixture of eggshells and a fluid which contains calcium acetate, and we have to separate it, and we can separate this by filtration. So we have to use a filter, and we can filtrate this part. So I have already done that because in the first place it takes very long to do this filtration, and two, it's very boring to watch at a filtration. So I will show you the result of the filtration. Can we switch to the small camera? Yes, so here you can see the leftovers from the eggshells, and here you can see the solution of calcium acetate. Thank you, we can switch back. So the next step is to heat up the calcium acetate, and we use a burner for it. Here it is. So, and I think now the question comes. So, how does the heating up this solution affects the concentration of calcium acetate in the calcium acetate solution? So, once again, how does this affect the concentration of calcium acetate in the calcium acetate solution? So if you want to answer this, please answer the question, and then I will check the answers. So in the meanwhile, I will continue heating up my mixture. You can see that the fluid is boiling now. So some of the water evaporates now. You have to do this very gently, because otherwise the solution comes too high in the beaker, and then all the salt will get on the edge of the glass. We don't want to have that. So if you do this experiment in your classroom, you have to evaporate almost 50% of the volume, of the starting volume. Do we already have some answers, studio? Okay, Katrina says A. A, thank you. Okay, so the reason we do this is because we want to have the concentration of calcium acetate higher than the starting concentration. So we evaporate the water, and the amount of chemicals will be the same. So it's logical that the concentration will be higher. So now we have 50% of the volume, and now we can make the flammable gel. But first we have to cool this down, and I already did that, so because it takes too long otherwise. So here is my cooled down material, and now we are going to add 15 milliliters of alcohol. So can we please switch to the small camera, so the close-up? Yes, thank you. And now hopefully you can see that there is a gel formed. Thank you. We can switch back. So you can see there's some of the alcohol is still there, but there's also a big amount of gel. So, oh, the camera has moved. We have a big amount of gel. Of course, we have to test the gel. So I take some of the gel and put it in a glass, and then hopefully it will burn. Perhaps we can switch to the small camera. And there it is, very nice. Burns with a very blue flame. Very nice. Thank you. We can switch back. So I will put this. Perhaps a few viewers noticed that the color of the flame changed slightly during the burning. So the fun thing about this reaction is that when the alcohol was burnt, some calcium acetate decomposes, and then the reaction product will be acetone. And acetone is also a very flammable chemical. So instead of one burning material, we have two materials that burn. So that was more or less the performance that I wanted to do, but I have for you the reactions that took place. Alex, can you show the PowerPoint? Yes, so here you can see the different reactions that took place. The forming of the calcium acetate is the first reaction. The second reaction was the combustion of alcohol, and the third reaction was the forming of acetone. So, Alice, can you go to the next slide? Thank you. So I don't want to read this all to you, but these are the student activities that our students have to do by this experiment. I think it's a lot of chemistry in there. So if you want to look it back, this performance, and see what we do at our school with this experiment, please go to the YouTube channel where you can see this presentation, and then you can read this whole thing down. Alice, can you show the picture of the flammable gel we made today and used in our stove?
Thank you very much, Mark.
Welcome.
And we do not have a question from the audience, so let me briefly encourage our audience to ask questions. We will get to them at the end, because as it is our tradition, we will have a discussion session at the end where we will get to your questions, even if you ask them during our stream. And getting back to you, Mark, and I would like to ask you about finding your inspiration for new experiments. So, as you said, you come up with a lot of experiments to even touch on very difficult topics. Mm-hmm. And what is your mental process to come up with new experiments that would be engaging for students?
So, I'm a teacher now for almost 30 years, and the theory hasn't changed that much. and also the experiments haven't changed that much. So for me, it's more or less getting boring to do every year the same thing. So I search a lot for new experiments, new things, search the whole YouTube channel, every channel that broadcast chemistry lessons I visit. So I want to develop myself as a teacher constantly, that was the word, constantly. So yeah, that's more or less the reason. Not getting bored and getting developed every year as a teacher.
Sure. Thank you very much, Mark. I'm really looking forward to seeing you again in the discussion session, and we will get to hopefully to other questions there. And we can continue with the next performer. See you later. And I would like to welcome back Anya.
Hello.
Hey Anya, how are you doing?
Good, it's gotten a bit dark here, for a reason.
Yeah, and I think it's lovely to see you again. I think we could say that you are also already a regular at our Science on Interactive streams. But don't worry, that doesn't make you immune to our difficult questions. So let's start with one. We know that you prepare science shows for Science Gateway, a science center at CERN. And I would like to ask you, you have already prepared a few of them. Which one did you find the most challenging to prepare?
I think all of them are challenging in their own way. Some of them because of the age group, and some of them because they tackle such complex topics. All of the shows that we have here, they somewhat relate to particle physics, which means that we are talking about things that we cannot possibly see. Either that's particles or that's data. So, or that's cryogenics or something like that. So it's really difficult to say which one was most challenging. All of them were challenging in their own way, but all of them I am really happy to put on stage and really excited to do.
Maybe is there any particular experiment that you were not able to put on stage or prepare for, let's say, security reasons or safety reasons?
Whew. How do I say that? We've done an experiment that is absolutely fantastic for several months before our safety team came to us and was like, this is maybe a bit too dangerous. So currently we're updating that simple experiment with some, you know, high voltage and things like that.
Okay, and as you maybe have already noticed, we also try to showcase hobbies of our guests. And we have a short clip also from you.
This was not sponsored by any of those board games.
Yeah, I can confirm that. And getting from hobbies to reaction, and action and reaction is also a way of learning, right? Even also that for artificial intelligence and human intelligence. And I wanted to ask you if you think that board games are good for learning, and if you've encountered a good educational board game, as we've seen that the clip was about the board games, and you have a bookshelf full of it, or them.
I think board games are good for learning, definitely. But I wouldn't say that I found board games to be educational in the typical way of being educational. I think what we learn from board games is really more about how to, well, if I go with the topic of today's stream, how to interact, how to react to something happening to you, how to react, for example, to losing, how to react to knowing that you're gonna lose, or how to react to, you know, winning really well while trying not to, you know, make the others react by crying.
Okay, thank you, Anya. I will not postpone your experiments any further. So the stage is yours, and we're looking forward to your performance.
Okay, thank you. So yeah, I don't really have any fire experiments. So I hope it's still going to be interesting. What I'm going to go for today is something that we're using in particle physics basically every day. And I'm just noticing that this blur in my... Okay, this is better now. You can see my eyes as well. So I'm using something that we have in particle physics all the time. This is interaction of particles, invisible particles, with various detectors, making those particles detectable. So what I want to focus on today is reaction of one of those types of detectors. Specifically, I'm going to be talking about something called scintillation. But before we go into scintillation, because that's a very specific kind of word, I want to start with something that you might have heard before, which is fluorescence. Fluorescence is something that we typically use on the stars that we put on the ceiling as kids, that glow in the dark. Well, that's kind of phosphorescence, but let's ignore that part. So fluorescence is really glowing in the dark and things like that. It is something that we have encountered. And actually, fluorescence is something that is very, very useful also in our everyday lives. So I first have a question for the ones watching. Thank you very much for watching. Which thing is fluorescence not used for? So we have A, checking banknotes for authenticity, B, detecting scorpions in the desert, C, analysis of biological processes, and D, improving plant growth. I will answer this just slightly later, but first I just want to show you some really cool things that glow. Of course, I need to start with introducing a special type of light. We'll now turn off this screen. So the light that I have here is a UV light. UV is a type of light that is invisible to human eye. However, today you can see a bit of a glow because typically UV torches do have a glow for safety reasons, because no one really wants you to check UV light by looking at them directly. That would be a horrible idea, because UV light has higher energy than visible light. That means that it can damage the tissues a lot more. So we need to be careful, and I will make sure to always point this downwards and not in my eyes. So if you ever encounter UV lights, never point them towards your eyes. And I will start with what I already teased in at the very beginning. So the very first thing that I want to do is I want to show you why I don't wear any nail polish. So if you can see it now, or do I need, can you see the ends of my fingernails? They are in a slightly different color. Let me try it with the second torch that I have somewhere here. Yeah, this one is going to be better because it's not as bright. So you can see the ends of my fingernails are fluorescing. In fact, many different things all around us are fluorescing. For example, you've probably all played with markers before. I have one orange marker here. Nothing special in the dark, but you can really see it glow once I put it under UV light. The same thing happens to many different toys, like this one. And I even found some pencils, like this one over here. What you could see also in our everyday life, well, maybe not so everyday life, is something that's, well, Blaž is already hinting at in the chat. So in a club, if you go ever to a nightclub where they have so-called black light, now what we get is we get fluorescence of white stuff. So for example, one thing that fluoresces would be, of course, fabric. I have white string over there, and typically also our teeth. So teeth are also nicely fluorescent, so you can see them looking really scarily now in my mouth. So this is one of the things that happens in a nightclub. So if we're using the so-called black light, typically in clubs, what they would have is a black light that is not such a strong source of UV light. So of course, it is safe to dance in a club that has UV light, but I wouldn't necessarily recommend looking into that light source. So that was it for fluorescence. Well, the first part of the fluorescence. And before I continue to scintillation, I just, of course, want to answer the question that we had before. And indeed, as my favorite experiments, or otherwise known as Michael, said, fluorescence in some ways is used for all of them. So actually, one of them is not direct use of fluorescence, and that would be helping plants grow. That is a common thing, that people think that fluorescence would make them help grow. Of course, we can use fluorescence in the light bulbs that we're using, but that does not directly impact how the plants are growing. But all the rest are something that we can use fluorescence for. I was especially surprised by one of them, which I will now just quickly share. Share screen. It takes a bit of time. Screen. Nope. I want the other screen. So this was shared with me by a dear colleague of mine, whom I also saw that is following this stream. So that would be Derek. Derek lives in South Africa, and one of the things that he shared with me is that what glows in the dark are also scorpions. And I have no idea if you can see any of that. So I'm sharing a picture of a scorpion. I have no idea if you can see it. If you cannot, then you can Google it. You are sharing. Stop sharing. Let's try it again. I always have some technical difficulties. That's how CERN goes. If you're at CERN, there's going to be a technical difficulty. Anyway, so scorpions actually glow in the dark, and you would see them fluoresce in a desert if you're searching for them. Okay, so I'm now going to continue with I'm going to change into scintillation. So when we're talking about fluorescence, what is happening is a material gets a high energy light, for example UV light, and transforms that into, so it reacts to that by absorbing it, and then it emits light with lower energy. When we're talking about scintillation, scintillation is a similar process, but we're not reacting to higher energy photons necessarily. We also do, but not only that. We are reacting, well, the material is reacting to ionizing radiation. So kind of connecting to what Adam was talking in the very first show. And here I have, for this, I have two, I need to do it like this. Check before. Okay, I have two different transparent blocks. They look basically the same. They look both like plastic. One of them is slightly dirtier than the other. That's because one of them has been used a bit more often. And one of them is special, while the other one isn't. And I'll have to, again, turn off the screen on my computer. Like this. Okay. So I have my UV light. Again, works with the toy very nicely. And now, if I go over this one here, you can see that basically there's nothing really special happening. But if I go to this one here, you can see a really, really, really nice glow. This is how at CERN and elsewhere as well are detecting ionizing radiation, or actually we're using this to detect the energy of particles. When the particles deposit their energy, they emit ionizing radiation, and that ionizing radiation causes our scintillating crystals to glow. In this case, is of course a nice blue glow, but I also have another piece of plastic that looks like this. It's a bit more yellow, and this one glows even better. It glows so much that actually I am now illuminated as well. So only by getting light out of things like this, we can measure how much energy particles have when they're emitted either from a particle collision or from a radioactive source. And just so I don't only show you how it happens with light, I can't show you how it happens with particles because they're busy being accelerated around CERN at the moment. What I can show you is an actual example of this crystal. These crystals, so the one that I showed you before, those are plastic scintillators. Crystals like this are used in our detectors. So this is used in one of our detectors called CMS. This piece over here, what is fantastic about it is not only that it's scintillating, but also that it is 86% made of metal. So 86% of this is metal. That makes this rod really, really heavy, but still it is completely transparent. Of course, once we have ionizing radiation going through, what we would get is we would get photons coming out of this crystal. These crystals have to be grown, and they're growing for several days before we can get them to this final size. And for the end, just because I think it's really popular to end a show with some fire, I have a nice little candle here. This is all that I could improvise very last minute when I saw that people are doing fire. And because at CERN we have to be really safe, I'm not allowed to really use fire in my office, but I can make the candle glow slightly differently. Anyway, that's it from me. Thank you very much.
And thank you, Anja, for your demonstrations. And I think you can turn on your lights for this session to continue, or if it is
just
inconvenient.
a second.
Yeah, perfect.
I'm now slightly blind.
No worries. And we did not, unfortunately, see your shared screen, but we did see a little bit of the picture in the reflections on the blocks and on the whiteboard. And I would think it's something like this, right?
Yeah.
Yeah. So these are from Google, which were you referring. And I believe we have a question from our audience. So let's look at it. And the question is, I was thinking about using fluorescence of chlorophyll to indicate the capacity for photosynthesis, which is also indirect but can help be a measure of plant growth. This does not end in a question mark. So the question
it's not a question. Yeah, it's really there is fluorescence, but fluorescence per se is not influencing plant growth in that case.
Yeah. So the question would be: is that a good idea to follow through, or to? Okay, so I think the question was, can you comment? And you did comment, so let's continue. We have another one.
Oh, the crystal. The crystal is a part of a detector at CERN. Sorry, I have to put my gloves on to show it again. And the glove is inside out, huh? So it is called lead tungsten. So it is 86% metal. It looks like this. Mm-hmm. So it is a scintillating material that we use. Of course, we use this in our particle detectors. It is extremely expensive, extremely fragile. You can see it just by being moved a bit. Here it's already cracked. But it is a fantastic piece of material, and it weighs as much as a steel block.
Thank you very much. And we have a third one. And how much radiation would we need to see the scintillation on camera?
We would need quite a lot. I do not know the exact number, but just looking at detectors at CERN, we know that inside these detectors we have high levels of radiation. Still, when we have those level of radiations, we cannot see that light on camera. We still need something called photomultipliers, which would then enhance the signal for us to be able to see anything. So unfortunately, the only answer I can really give you, more radiation that it would be safe for me to bring here.
Okay, I can understand that. And the scintillation as a word was a new one when we were preparing for this stream. And internally there was another word that was floating around. So I wanted to ask you, and the word was radioluminescence. Is it an equal to a scintillation, or is there something different between these two terms?
I think radioluminescence, as far as I know, is the overall term.
Okay.
So it would be both also for fluorescence and phosphorescence.
Okay.
This is how it can be used, but typically at CERN we don't really talk about that when we talk about these three ways of luminescence in general. So yeah. Mm-hmm. Okay. But I can check and let you know in the end.
Perfect, perfect. We have a discussion session, so you can always jump in with answers. And also you, audience, can ask other questions, and we will make sure to ask them during the discussion session. So again, thank you, Anya, and we can continue with our stream. At the beginning of this stream, I promised you a special treat from Stuart. And now it's time to go through and show you what Stuart sent us.
Hi, my name's Stuart Cole-Hagan and I'm the Science Nomad. I'm very happy to join the team from Science On for their special on reactions. We've had to pre-record this because at the moment I'm actually working in China. Today, while we're doing the recording, it's actually Thanksgiving, but soon it's the special season of Science Muss. So I thought for reactions, I would introduce the three wise phenomena. One of the three wise phenomena, magnetism. Another one, electric charge. And finally, force and motion. So these are the three wise phenomena. And often in science, often in the world, where you have two of them, the third one is going to turn up sooner or later. It's one of the things I love about science and understanding its principles, is that sometimes you will find some principles that you understand in one area are actually working in some other very different areas. So principles you understand in biology can turn up and help you understand chemistry, can help you understand physics. And so for tonight's quick session, I thought I would play around with the three wise phenomena in some different demonstrations and kind of see what kind of a reaction I can get from you. Let's go and have a look at the bench. One of the little demonstrations I wanted to share with you is this. You've probably seen something like it. Just a series of coils of copper wire, and one end connected here to the positive, the other end connected to the negative of a power supply. So I can apply a voltage to the coil. Because this is copper, it's a conductor, and conductors have lots of free electrons. They've got electric charges that can be moved if you apply a voltage. The other part of the activity uses a small magnet with a couple of nails stuck onto it. So just a very small magnet, some nails stuck onto there. They're made of iron, so they will stick on quite well. And when we put the little magnet with the nails in the middle, you can see it's quite free to spin. Let's just see what happens when I put a voltage on to this little device. We can see there immediately our compass, our magnet in the middle, jumped. It moved around. I just turned it off and it relaxed. We'll try it again, and it moved. As I mentioned, the copper coil is full of electrons. They have electric charge. When we apply the voltage from the power supply, that actually puts those electrons into motion. They start flowing. We create an electric current. As soon as we have the electric current flowing in the coil, we generate a magnetic field. And that magnetic field in the coil then creates a force back on our little compass in the middle, making it move. So that's just one example of how these three principles interact. Here's another simple demonstration of those principles. We have a toy motor, a gearbox connected to a wheel. When I put some voltage across the motor, not surprising, we get it to work. So again, we have the electric charge of the electrons in the coils, in the copper in the motor. We put those in motion by applying a voltage. That generates a magnetic field that in fact reacts against the magnets that are already in the motor, leading to more force, movement coming out. And so it's the same principles turning up again. But we can see this actually now working in reverse. We have two motors, the same, hooked up. We've seen how one works as a motor, but if I hold on to this and I put the motion in, what was a motor is now a generator. So here I'm putting in the force, my energy, rotating it, moving that in a magnetic field, and that's then generating the electric current, which goes to the other motor, where the process is reversed. So a generator and a motor, it's the same three principles. So let's take a step towards chemistry. Here, in a tank of salty water, I've got two carbon electrodes. They're actually the leads out of a couple of pencils, and I've got them connected to a power supply. And at the moment, I'm just slowly increasing the voltage between the two electrodes. And here we see the start of hydrogen coming off one of the electrodes, and the voltage as it goes up in a moment, we'll see oxygen coming off the other electrode. We understand this is the electrolysis of water. But what we often don't think about are those charged particles moving between one and the other. We can't see them. And we also don't really focus on the chemistry, not the real chemistry of what's happening. So here we are tearing water apart. We've got hydrogen leaving, and we've got oxygen evolving at the other electrode. But in our classes, we tend to just talk about the electrochemistry of what's going on. There's a lot else happening. And one of those other things which is going on is to do with acids and bases. We're taught a lot about acids and bases in high school chemistry. We're introduced to the concept of pH. One of the things we often don't focus on is pH is really a concentration of hydrogen ions. That means it's a charge. And so all the other things we've been talking about today are to do with charges, motion, and magnets. So I've loaded vinegar into the top channel, labelled acid, and I've put ammonia into the lower channel, which will now be caustic or basic. I'll add some blue pH indicator, which I've made from boiling up red cabbages. And we can see that in the acidic liquid, the indicator goes bright red. In the base, the indicator will turn green. But remember now, we're actually looking at ions, charged particles. That's giving us the colours. And that's important in our next activity. So we've looked at acids and bases and electrolysis and charge and magnets and current. Here's a tank with 2 electrodes filled with salty water and a pH indicator. Here is a small strong magnet that I'm going to put under the tank between the 2 electrodes. So it's not in the water, it's not touching the electrodes, but we have a magnetic field now coming up through the water. I've also got a little stand to hold a couple of other magnets, which I'll place. There's a gap under the bottom, which allows the fluid in the tank to flow and pass between the 2 electrodes. So now we have a very strong magnetic field that's going top down, and we're able to pass a current, that current that we saw electrolyzing the water. Now when we apply the voltage, we see a number of things happening. We can see bubbles, we can see the color changing, and we can see very rapid movement. That's movement across the tank. So all of this is happening even when we don't see it. So as we electrolyze the water, we're making charged ions, and those ions are moving, but they're moving with a magnetic field on top of them. And so that results in another force, which is pushing that flow across the tank to the right-hand side. We can see the color is changing, and that's telling us the pH is changing. And we know that because the hydrogen is bubbling off. We're losing hydrogen ions, so the pH has to change. This process is called magnetohydrodynamics, and it's actually used to pump coolant through nuclear reactors. But for me, I think it's just beautiful.
I would like to remotely thank Stuart for bringing us the atmosphere of the upcoming festive season through the 3 WISE phenomena. Unfortunately, he could not be with us tonight, but if you have any questions or comments, you can definitely post them in the discussion or the comment sections of our social media, and Stuart will definitely get to them once he gets to some solid VPN. And continuing and talking about our social media, this is our 4th international science stream. And as we wanted to cement our position at the international science community, we did the most obvious thing: we created an English-only YouTube channel. this YouTube channel is for performers, but also for you of our international viewers. So if you want to engage with the performers even outside of these streams, you can do so in the YouTube channels, in the comment sections, and our dear performers and guests will answer the questions there. And after this short break, we can continue with our live stream with the next live performance. And the next performance will be held directly here in the studio by David. Welcome, David, back.
Hi.
And David, we know that your hobby is climbing. Right? And the first obvious question, what do you prefer more, indoor or outdoors?
Oh, definitely outdoors. Definitely. I am scared like indoors.
Are you?
Yeah, it doesn't make any sense because it's like safer when you climb indoors. You have like concrete walls and specified paths which you can climb. You have like the help is always close, but still I'm scared indoors. Even when I'm in the nature, I can walk, I can climb even without a rope, and I'm fine.
And for example, do you have any specific goal, like next mountain you would like to conquer, or?
I'm really not a mountain climber. I'm more a rock climber. So it depends. I would love to go back to the sandstone rocks that we have in western Czechia. So this could be my next goal, to visit it once again.
And in the tradition of connecting hobbies and reaction, I would like to ask you, have you ever experienced a situation in which quick reaction was crucial for like surviving?
In climbing?
In climbing.
Always. Always. Yes, there were a few times that I fell or I was falling, and if you're not fast enough to react to that you are falling and you jump off the wall, or you don't jump off the wall, you can slide down and just get nice scars and bruises all over your face.
Okay, and how high was that?
Well, 20-25 meters, I think. Yeah. But the fall wasn't that high, it was like 7 meters.
Oh, yeah, but we're definitely glad that you survived that, thanks to the quick reactions. And some other reactions, I hope you will show us in your experiments, right?
Yeah,
so the stage is yours.
Thank you.
It's up to you.
Okay, thank you. Welcome. Welcome to my improvised lab. And as I mentioned before, I have a problem which most of science students face during their study at the university, and a few people can face it even in their professional work in the laboratory. And that is that you have samples without names. And they look pretty same. Both of them are white, they're crystal, they're solid. Both of them form crystals. They both reflect light. But one of them is urea, and the other one is sodium hydroxide. Urea is pretty, it's not dangerous chemical. You can even eat it. It's normally inside your bloodstream, inside your urea tubes, etc. But the sodium hydroxide isn't a substance which you would like to try to mess with, because it could burn or dissolve your flesh, and it's not really a pleasant thing to make holes in your body. So, but I said I'm in an improvised lab, but obviously I'm not in a lab, so I don't have machines or some sophisticated methods to find out which of these is which chemical. But I still have water, and my question for you is, what will happen when I mix these substances with water? So one of them is sodium hydroxide, the other one is urea. So what will happen? You can see the choices you can choose under the under me. So either you will see change of color, or the change of temperature, or the mixing process will create some bubbles, or the easiest one would be that one of these chemicals dissolves in water and one doesn't. So choose which you think is correct, and I can, while you're answering, I can show you more closely the chemicals. I have here water glass. So here's one of them, and here is the second one. Yeah, you can see that one of the first one has bigger crystals, and the second one then has some smaller still crystals. Both of them are white, both of them are solid. Without smell, the taste is hard to define because you wouldn't like tasting sodium hydroxide. But we will try to mix them with water, and my question was what will happen, and I would like to know if anyone answered. So what are your answers? A or B, so change of color or temperature? B, in my opinion, yeah, change of temperature, maybe. D was, I don't remember what was D. Under D was, yeah, that one will dissolve and the other one won't. Okay, it is possible too. B, again, change of temperature. Okay, we will see. We will see. So, the change of color would be pretty obvious. If I start mixing the compounds, the water should change color. But I want to show you, before I start mixing it, the temperature of the water that we will use to mix. You can see it in this corner, and it will stay there, so you can always see it. Maybe we'll use it, maybe not. It's nice to have it there. So I'll put my safety glasses on, and I will put some water in the beaks. Just enough. Okay, it's almost the same amount. Okay, so now I will start with this one, with the bigger crystals. And because it could be hydroxide, I need to stir it pretty well to avoid it splashing into my face. Okay, and while I'm stirring, we can watch the substance dissolve. I will turn the beak so you can see it more like better. Yeah, most of it is gone now, so I will add more. We are like halfway through, and it still dissolves. Okay, so I'll add even more. I'll add all of it to half of it. Okay, so I have put all of unknown substance in our water, which currently has 27 degrees. I have the thermometer in the water here, in the container from which I spilled it. All right, so you can see that most of the crystals are gone. We have a small amount still undissolved. And we can try to dissolve the other one. So I will take it, open it, and repeat the process. So here I go. Again, because it could be hydroxide, I have to stir it pretty well. And could I do it the other way around? Like putting the water into the hydroxide or possible hydroxide? I think that's one of the basic things everyone learns in school, that you always have to put acid in water. But what about bases? Because hydroxide, if it is hydroxide, is a very strong base. And it works the same for bases and for acids. So you cannot mix bases or acids with water the way that you put water into them. Okay, so now you can see that even the second compound is dissolving. But you can see even change of color, possibly it turned white, but it's not the color that it changed. There are pretty small bubbles that are floating in the solution, in the water. So one of the correct answers was that that it will create bubbles. But it wasn't completely correct because only one of these substances created bubbles in the water. Well, you can see that both of these substances dissolved, so the D wasn't correct. And as I mentioned, the change of color isn't it either. So if you answered bubbles, or if you answered bubbles, you would be partially right. But what about the temperature? As I said, the water at the beginning had 26.5 degrees. You can still see it, see the amount here. So I will start with the first substance, or first solution with the substance. And we can see if the temperature will change. Yeah. And you can see that the temperature is falling down. So, and it stops around 16 degrees Celsius. Okay, so we started at 26 degrees Celsius and it ended up at 16. So this is the first substance, okay. And what about the second one? I will clean this and put it in the second one. Yeah, now you can see the temperature rising pretty steep. I will stir it a little bit more because there is still a bit of the substance in the crystal form. Okay, so now you can see that this substance has 42 degrees Celsius. So again, around 15 degrees centigrade up. So if you knew which of these substances changes the temperature one or the other way, you could now know, you would now know that the substance with the big crystals is urea, and the substance with the small crystals here with the thermometer, which is warm now, is the hydroxide, sodium hydroxide. The change of temperature here
is because the chemical, it could be because chemical reactions can be endothermic or exothermic. What it means that each chemical reaction, or most of them, either need heat to start the reaction or to perform the reaction, or they release the energy in form of heat, so they heat up. So dissolving of hydroxide could be exothermic reaction because it turned warmer, and dissolving the urea would be endothermic reaction because it is colder. It needed the heat in the water to dissolve. But there's a catch. Chemical reaction, or one of the sentences that describe the chemical reaction is that in a solution, in reactants, bonds have to break, and the new bonds have to be made, so it is called chemical reaction. You destroy one compound and form another one. It is partially true for one of these substances. The hydroxide, if you dissolve it in water, it separates ions of O and H and Na, and it kind of works here, so it could be partially chemical reaction. But with urea, it doesn't break down. Okay, the urea stays the same as it was from the chemical point of view. So it isn't, dissolving urea isn't chemical reaction. It is a physical reaction, so as with the hydroxide. Because we are turning the state of matter, we are turning from solid state to aqueous form, which is dissolving a crystal in water and making a solution out of it. You can possibly, most of you don't have urea at home, so you cannot try the cooling method. But I think and I hope that few of you, or maybe even more, have to unplug their drains from time to time. So you have to take some powder in a plastic bag and throw some into your drain, and then put warm water on it, and it cleans the drain. Well, you happen to have sodium or potassium hydroxide at home, so you can try this one. And for the cooling one, from the endothermic reaction, you have chemical 2, you have salt. But if you are dissolving salt in water, you won't see any difference, you won't see any change of temperature. You will need ice. If you take ice and mix it with salt, you can feel it for yourself, if you hold it in your hand, that the substance or the mixture will slowly cool down. Even when you start at 0 degrees centigrade, as the ice melts, when you add salt, it will be cooler and cooler and cooler. So just like that.
Thank you, David, for your interactive demonstration that we could see the temperature live. It was really great. And we do not have a question from our audience, so I will ask you personally. And I know that you just graduated biotechnology, is that correct? And you just showed us mostly chemistry in this experiment.
Yes.
And some people used to go to study a subject to avoid some other subjects. For example, you could go study biotechnology to avoid chemistry, for example. That could be in other biological subjects. And how was it with you? Did you always were able to be passionate about chemistry to pursue your other dreams, or did you have to find your way to chemistry?
I had to find my way.
At high school, I had problems with chemistry. It was one of the two subjects that I was receiving like
bad marks.
Yeah, bad marks, and even for my final evaluation, it was bad. So yeah, like for first 2-3 years, I was like fighting with chemistry, but then I had this like awesome teacher which showed me the way to chemistry, and I developed a love for the subject, and here I am today, and I love it even more.
Okay, that's perfect, because we love when experiments are interdisciplinary, so they cover more disciplines, and it's a perfect way for us to connect different people and through different disciplines. Thank you very much, David. And we're looking forward to have you during our discussion session, which will be a bit later, because we now have in front of us our last performance. And the honor and responsibility to close our stream tonight came to Sarina. So welcome back, Sarina.
Hi, thank you.
And so you are actually the only performer today that is for the first time with us during the stream. So hopefully not too nervous about what you have seen already through the streams or through the performances of other performers.
Well, I'm a little bit nervous, yeah.
Okay, it goes with that, always.
Yeah.
And so no worries, I think you'll be great. And I would like to jump right to the hobbies part, which is my favorite from these introductory interviews. So let's show a clip.
So you did some research, huh?
Yeah, I mean, when we were preparing for this stream, we jumped into a kind of a rabbit hole of the horse riding and all the disciplines that go with it, as we were totally unaware of them. And we figured that there are very diverse words describing the disciplines in different languages. For example, in Slovak and Czech, the discipline where the horses jump over the obstacles is called parkour, which, yes, is the same word as for freerunning, and yes, it makes some confusion between parents and kids when they're talking hobbies. So I would like to ask you to clear things up a little bit for us. So what kind of disciplines did we see in the clip, and what is it called in English and in Dutch?
Okay, so what you saw in the video is dressage. That's how it's called in English. And in Holland, we call it dressuur. So you have to dance with the horse, you have to interact with the horse, and the reaction you get from the horse has to be big, but your reaction to the horse has to be small, like with tiny little, how do you call it? Signs. With tiny signs, you have to have a big movement. So people don't see you do anything, but the horse does everything. So that's the art of dressage, I think. Yeah.
Yeah, and you jumped ahead a lot, because I wanted to ask you what kind of reactions you are experiencing when riding a horse. So I would like to ask you now to make sure that you are sharing your screen. So this is not a question. This is a request.
One moment, I will share the screen, okay? So I'll be back.
And they put me on screen, like full screen, but they did not give me instructions to what to say. So that's a great situation, which I'm in. And hopefully Sarina will get back soon with the presentation. So hang tight. And these are technical difficulties that we experience in every stream. And as with being nervous, it just goes.
Okay, I think it's set up, so we can start.
Perfect. So you just said it. We can start. The stage is yours.
Thank you. So yeah, I have the honor to close this performance, this nice live chemistry, and I promised you guys something about nail polish. So this is the nail polish I brought with me. It's red, and as you can see, I love good nails, and sometimes they are red and sometimes not, sometimes blue. And I thought, okay, what can I do with nail polish in my school with my students and get to theories where you can explain a lot. So that's what I want to show you. We all know that when we have nail polish on our nails, we can remove it with a solvent. And the solvent we use for nail polish is acetone. So I will put some nail polish in this cup, and I brought some acetone with me, and I will pour the acetone with the nail polish. As you can see, we get a nice solvent of red polish and acetone. And yeah, the weather here is terrible, so we love the colors, because here it's raining for almost now several weeks. So when you can give the classroom some nice colors, it's very cheerful. So now I have a nice red fluid, and yeah, when we have nail polish, we can't remove it with water, but I also brought some water with me, and this water is of course transparent with no color, and I want to give it what color before I show the experiment. So I will put this off, and the color I will use is blue. It's a color for food coloring, so you can use it in cake or bread or something to make in the kitchen. A little bit, and I put some water in it, and then you see a nice blue color. So the next question will be, what if I mix these two up? What will happen? So the question can go up. My screen is shared. Very nice. The question for you guys is, what do you think will happen when we mix these colored fluids with each other? So blue water and red acetone. What will happen? So that's the start question. So what will happen when we mix these two together? You can choose from A, the red acetone will sink under the blue water level to the bottom, or B, the red acetone will float on the blue water level, or C, the red acetone blue water will mix perfectly and give the mixture a purple color, or D, the red acetone and blue water will mix perfectly and give the mixture a green color. So I'm very excited to your answers, and I will go further with my experiment, because when I mix these, I want to have two of the same the same volume. So the red acetone will go in this, and I will use approximately 15 milliliters. And the blue one also. Nine. Okay. So it's better. Also 15 milliliters. So a red fluid and a blue fluid, and now I will mix them together, and then we'll see what happens. The red one, the acetone with the nail polish, and the blue one, and I will add it. As you can see, it mixes up perfectly and it gives a little bit of a purple color. Yeah, the blue color was like this, and the red was like this. Dichterbij, yeah, okay. So I don't remember which is denser, but I don't think the hydrocarbon is miscible with water. Okay. So Mark, what does that mean? That they won't be mixed together?
Yeah, I don't know which is denser.
Well, the density of acetone is lighter, if I remember it, than water. But they mix well together, so we don't get the two layers. Okay, the next question will be, wil jij op een pijltje drukken? Oh, some technical problems. Doesn't work anymore. Okay, Mark will try again. Yeah, another. Yeah. Okay, you can share it for me, please. Okay. Okay, the next question, I will just read it. The second question is, what will happen if we add salt to this mixture? So we have this mixture. What will happen if we pour like 4 spoons of salt in this glass with a mixture of acetone and water? Let me see. I will just pour it like this, that's better. So I'll put a lot of salt in it. And hopefully Mark can find the presentation with the animation to explain later what is going on. So I pour some salt in it. Now I will mix it better. And David earlier told us something about salt and what it does when you put it in water. So I will put another. Mix it again. And it takes a little while to start up. And now we have to wait. And this is always a problem also with my students. You have an experiment, and sometimes it don't feel like doing the things you want it to do. So I will take the other one I made earlier, and maybe this one, we'll check this later. But what we get is the following. I hope this will make the light back. As you can see, the mixture is separating from each other. The red will come on top of the blue. The blue was the water, the colored water, and this is the nail polish with the acetone. So the salt interacts with the mixture and let it separate from each other, but not like 50-50. Yeah, I had 50 milliliters of water and 50 milliliters of acetone, and you see the separation is a little bit higher, not like 50-50%. So now I will ask my student, what is happening? Why are these two separated from each other? So that's the question. What has happened? We know that water molecules can bond to each other with hydrogen bonds. You see it like in the animation. And acetone has like a carbon skeleton with non-polar, but the O atom is polar. Water is also polar, and we know from polar and polar that they mix well together. And the structure formula is from both of them. You see in the screen, they can form bonds to each other because the acetone has an O in it, which is polar, and water molecules are also polar. So click the button, please, and you see that the line between the H from the water and the O from the acetone molecule will find their way to each other, because the H of the water molecule is a little bit positive charged, and the O of the acetone is a little bit negative charged, and they will find each other by interacting, because positive and negative will search each other up. Okay, so I have an animation. This animation shows the water molecules when we have only water. When we pour acetone in it, they will mix well together because of the hydrogen bonds. But when we add salt, the interaction changes between the particles. David already told us that when we have salt and we solve it in water, the bond has to break. And when the bond breaks from salt, the ionic bond, we have a positive nitrogen natrium ion and a negative chloride ion. And the water molecules will search for these particles. The water molecules from the sodium ion will go like I forgot it. They will hydrate the ion with its oxygen atom. So when you have a positive charge, the O atom of the water molecule will find its way to sodium ion. And in the chloride, it's the other way around. So the hydrogen bonds will break down, and that will bring the acetone molecules again to each other. And because of the density, they will go on the upper layer, and the water will go down at the bottom. So you see here, left from the screen, the solution I created here, and in the right where you saw, yeah, on molecule level what is happening. Okay, so that was my animation. So this one separated from each other. The one I made earlier, it's a little bit less, but it worked also, as you can see. And you can do this with other colors. Here I also have one. This is the water, this is the acetone. It was also, it was blue polish, nail polish, and this was yellow food coloring. And when we mix these two, you get green. And here is the salt already added, so they will separate immediately. So I think that was my experiment. We can go back.
Thank you very much, Sarina. I'm so sorry that this was such an adventurous premiere for you. Yeah. But I think you pushed through each and every difficulty you had gracefully, and we saw great visual of the separation, even of the original solution. So I think it ended up pretty well. And to be a little bit easier on you after all this, let me just ask some easier questions. And the first would be, when and how did your interest in chemistry start? Was there a particular event or a professor, for example, teacher, that sparked an interest in chemistry for you?
Yes. When I was at school, there was a teacher, like a chemistry teacher with long gray hair and a long gray beard and some glasses, really a chemistry teacher. And he interested me in this chemistry because he saw me, and yeah, that really pushed me to go further with chemistry. So it was a teacher who, yeah, really get the best of me, something like that.
Yeah, the best teachers can do that. That's perfect. And the second one would be that Mark already told us a little bit about how he approaches the experiments with students. So I wanted to ask a similar question to you. And what do you think are the best methods, or the methods that work best to engage students in the experiments? What is like the secret formula for an experiment to be engaging for students?
Well, I think if they see something, they get an interest in why does this happen. So I hope always with an experiment to get a reaction from, oh wow, how is that possible? And when I do this, and then, oh, what are you doing? Show me. Then you get the interest and you do it, and then there is a nice theory behind it, because this experiment is a really easy experiment if it works, and you can get a lot of theory behind it to explain, for example, hydrogenation of ions, but also the structure, the molecule structure, what is happening in the molecule structure, why there is a positive charge, why is there a negative charge, why do they work well together. And yeah, I really use this experiment for teaching the children what kind of type of bonds you have in particles. And yeah, I hope it's engaging for the students.
Mm-hmm. Do I summarize that well if I say that the method is the experiments that inspire curiosity? So yeah, if it inspires curiosity and the students start asking questions, that's a good method for engagement. Is it correct?
Yeah.
Oh, yeah. Thank you very much.
Thank you.
Thank you for your experiment. I think it was visually very pleasing. And as I mentioned, this was the last performance, but it's not the end of the stream because we have a discussion session following very shortly. Thank you, Sarina, and see you soon.
Yeah, bye. Thank you.
And before we start the discussion session, I would like to invite you to our next stream. As I mentioned, we stream every month in Czech. So the very next stream will be in Czech and will be on the 12th of December. The theme for the upcoming stream is trick. We will have some mainly physics experiments. We will have a magician. And if Stuart did not inspire you enough for experiments that you can try over this holiday season, you will find a lot more in the next stream. And as I promised, the discussion session is coming now. And I have Adam with me here, David, and everyone from our virtual world and remote. We can also invite back on stage. So welcome back, Sarina and Mark. And welcome back, Anya. So I would like to start with the questions from our audience. So if you could get the first question, please, up on the screen. And is the question for Adam. I'm looking for some simple, cheap, safe radioactive sources to use as part of science show. For example, potassium chloride. Do you have any favorites?
Many. There is a lot of like rocks or minerals which are radioactive, and these are safe and legal, of course, because there are not many interesting and legal stuff out there, but the geological stuff are in general legal to have in Europe, at least. I don't know the other parts of the world, but in Europe you can have uranium ore, you can have the thorium mineral, and other things like radiobarite. It's also interesting mineral. And I write an article in Czech about radioactive sources which can be used in school, for example. So, but it is in Czech. But you can use the tritium pendant. It's often, or the welding rods with TIG welding. And there is a thorium, and also uranium glass you can buy. It's not that hard, and it's legal. And
what's the best place to find best place to find this radium glass?
Radium glass, you can buy antique, of course, but you can even buy new things from uranium glass. Okay. And this is like the interesting things, I think.
Sure, and if anyone is interested in more concrete tips, then go to the comment section, and Adam will try to find you even more.
Yeah, I got a lot of tips about everything, and I got tips for illegal things and for illegal things and something between. Yeah.
So message Adam on private channels if you want the illegal stuff. Coming back to questions from us. I have one for Anya, and I would follow up with sure. And at the end, we did not have fire because of the safety regulations of CERN, but we did have a very wow effect ending from your side, which was the candle. And I was just wondering, did you just wander around before the stream with your torch trying to find something that would light up, or did you know about the candle before?
I absolutely love this question because I now have to admit I just wanted to create an urban legend that candle stems glow in the dark. I actually used a pen. So it's a glow in the dark marker.
You got us all.
Yes.
Thank you, Annie.
But I failed. You figured it out that something was off with that, yeah.
Thanks a lot. Going back to the questions from audience. Eric asked, does anyone have a source for the proton and neutron spiny sphere models available in the USA? So the sphere models were part of Adam's experiments, is this correct?
I think. Yeah, it's like it's a kit for children, which is called Thorn Balls, and you can buy it. It's for kindergarten children, but I use it for my models of nucleus. So you can buy it legally.
So, okay. So if you want to find that, Google foam balls.
Thorn.
Thorn,
like spikes.
Yeah, thorn balls, and hopefully you will find it available in the USA as well. Do you have another question from audience? Okay, David asks, does the acetate change in a chemical way when it heats up during the burn? David, was the question from you on 2?
The first performance. I'm sorry, I just didn't remember the name, but yeah, it was you.
Mark,
sorry.
First online. So
Mark, I think.
It was for Mark.
Yeah.
Mark, could you please answer the question?
Yeah, I can, because I already saw the question and I wrote down the chemical equation on the board. I hope you can read it.
Yeah, right.
We can now.
Thank you. And there you can see that the acetate actually really changes because of the decomposition, and it forms acetone. So yes, it's really reacting, so it's really changing.
Okay, so as I see, it makes a line. Is it CaCO3? Oh, it doesn't matter. Okay, so as it burns, it slowly turns into acetone and CaCO3, and the acetone even burns during reaction.
Yes, exactly that. Yeah.
Okay, thank you.
Okay, thank you very much, David. You just did what I wanted to ask next, and that is if you have questions for your fellow performers. So I would just ask Sarina, were you able to follow other performance experiments, and did any questions come up to your mind while we were watching them?
Yeah, I really find it interesting to Anja, because when I think of a metal like iron, you can't see through it, and we already asked the question. Implied it. Why is it transparent? Why can you see through the metal? That's really, I have an error in my mind.
That is a very, very good question, and I was wondering the same just a while ago. So it's basically the main reason why we can see through it, so why it's transparent, is its crystalline structure. So the structure of the crystal is just right that allows the photons to pass. So that's only the main reason. In addition, you also like this structure also makes it so that we don't have any free electrons that would interact with the photons. So it's really many different reasons altogether, each of them having a small effect next to it, but finally coming to something that is absolutely completely transparent, which is absolutely fantastic.
Yes.
And I also saw before that there was another question connected to this as well. Yeah, this one. So is there any particular reason why does the crystal have to be made out of metal? Again, there's several reasons. One of them is, of course, very simple. We need to have a dense material for the particles to really deposit their energy in the crystal. So it has to be a dense thing in order for that to be useful for us in terms of scintillation, because we need to have that effect of particle stopping to get the energy. So yeah, that is one of the reasons. And of course, having the metal there also helps with the stability and everything.
Now, I might have a follow-up question. Would any metal work? What kind of metals would work, and what kind would not?
So there's several different ways of creating these scintillators. And yeah, it's not, I don't think it's any kind of metal, but this is something that I wouldn't really know. But I know that there's many different types, many different metals that we can use. For example, the one that I showed, that is lead tungsten. And in some others you would have also some other metals. Interestingly enough, it doesn't need to necessarily be a solid. In one of the other experiments at CERN, we're also using gases.
Okay, thank you. And I would like to ask a similar question that I asked David, and that was about going into different disciplines, maybe for inspiration, maybe just out of curiosity, and sometimes to exactly to go forward with your own research or your own profession in a different way. And I would like to ask Sarina, do you usually go for inspiration outside of chemistry?
Outside of chemistry?
Yeah. So do you follow, for example, experiments in physics and other areas that may not be connected to chemistry directly, but you can find inspirations for experiments there?
Well, I teach also some physics, but in the lower part of the school. Yeah, and physics and chemistry are everywhere. Yeah, when you go outside, it's always there. And the inspiration I really have is standing here next to me, Mark. And sometimes I inspire him, but most of the time he inspires me. And yeah, when you are at home and you're scrolling down your phone and you see something, then I will send it to him. Hey, look at this. Maybe it is something, and the other way around. And then we move each other to look forward and to look how we can put this in the classroom. So the biggest inspiration is right here.
Okay, great.
It's nice to work. It's nice to work with this guy. Yeah.
I can definitely imagine. And we have a question from audience. Can we get it up? And it's a question to Adam, again from, I believe it's Michael, right? And it's very, and he asked you, did you say you wrote an article on this? Can you share the link? I know you said it's in Czech, but I can write it through Google Translate.
Yeah, I can send it to Michael. Yeah, so.
Okay, so
just write me on Facebook or anywhere else, and I will send the link.
Okay, so that's done. And I would also like to follow with a question to your peers. For example, Anya, were you able to follow other performers, and did you note any question that you would have for them?
I was actually really impressed by especially the last experiment with the chemistry, because I'm not a chemist, so with the separation of acetone and water. But to be honest, I'm cheating a bit. I'm using AI to learn what's happening in the back. So while you were explaining, I was already like Googling, ooh, can I see more about that? It's absolutely fantastic. So I just really love what you did.
Well, thank you. I was a little bit struggling, but yeah, in the end it works. I have it here, and yeah, it's also a technical issue, but yeah, what makes me more nervous than I already was. So, but it is nice. And the students also find it very interesting, so that's also nice. But thank you, Anja.
And I think it was you, Anja, that you had fluorescence and plants in your presentation, and mentioned that there is no known reason why plants should be fluorescent. Is that correct?
Not
did
that
I remember
know
it correctly? Oh, okay. Yeah, maybe I did not remember it correctly. It happens. So I wanted to ask a question which I found recently. That is, why are leaves green? Like usually green. You might find other colors. Because in a visible light that comes to us, green is actually one of the most prominent colors in the light. So plants would get most energy if they used the green light, but they decide to not absorb it and reflect it. And so I wanted to ask if anyone has any theory on that, why chlorophyll is green if it's counterintuitive when green is the most prominent. Sorry, Mark, did you have any theory?
Yeah, Mark has a theory.
I'm not sure. It's a while ago that I did study biology, but I thought there was an experiment where they give plants red light instead of green light, and then they function better. So the thing then was that plants need red light instead of green.
Mm-hmm. David, you seem like you are in a thinking mode.
Yeah,
so,
like I'm trying so hard to remember my classes in like flowers biology and biochemistry behind that. And I most of the pigments in flowers, which is responsible for photosynthesis, have like peak absorbance in red light. Why? I don't know, but I know that it's true.
Yeah. And you know what to do if you know from our audience. You have to go to the comment section and clear that up for us, because none of us knows. And I believe we have another question from audience. Teresa asks, is there a substance that when dissolved in water causes such an endothermic reaction that the water freezes? I think it's towards David, because he had a similar experiment, but I think Mark and Sarina could have some comments. So David, would you like to start?
Yeah.
I can. I don't know any substance that if you mix it with water, you make the solution solidify. But if you use the urea, which I used in the experiment, and you use like little water, a lot of urea, and you put the beak with the solution on how do you call spilled water? It doesn't matter. If you put it on water, the solution can go as low as minus 15 degrees Celsius. So the solution itself won't solidify, but sorry, I was hearing myself in the I find it hard to speak. So the solution itself won't solidify, but the temperature itself would be so low that the water around it would solidify. So I hope it answered your question, but
yeah, Mark has a comment.
No.
Yeah, there's a very nice experiment where you mix. I don't know the amounts anymore, but you have to mix ammonium chloride together with barium hydroxide, both solid, and then you mix them. The starting temperature will be around 20 degrees plus. Then you start mixing it. One of the reaction products is water, and then a lot of reaction take place. The temperature will go down to minus 20. So there you have a real nice experiment for demonstrating endothermic reactions. Ammonium chloride and barium hydroxide.
Okay, thank you. And we have time for maybe two more, maybe bonus questions, bonus experiments. I believe that Adam had something prepared.
Yeah, I had something because I had something for Anya. Yeah. Because I made a scintillation detector by myself, like DIY, and I used duct tape and zinc sulfide. If you know
duct tape is what holds CERN together, so fantastic.
all the organizations, I think. Yeah. So I got a picture. Maybe you can show it. There's a DIY. Yeah, this is my DIY scintillator, and the middle pictures are the pictures of the light which was created.
Nice.
I use the source of radiation was ion chamber in old smoke detector. There is americium 241, and the setup is right here in the right down corner.
Fantastic.
So it's DIY. How to make DIY? You don't need large badass crystals.
Not that it's anything wrong with your crystals.
Yeah, but the crystals were amazing.
Shaming me for the size of our crystals, like.
I was amazed by that, but.
Okay, thank you. And I would like to ask again if any of you has a question for your peers. And if not, we have one. Okay, Mark, do you have a question?
Yeah, it's a question to Anya. Anya, can you share the method you used to build the simulation of CERN with Wim Hurst? Because I can't see how you made it. So it would be nice if you could share this with us.
So you mean the experiment I did 2 shares ago or something?
Yes.
So basically you have a ball, and then the metal it's a copper strip. So basically just a copper strip you connect in the correct orientation, and then it should work. Okay. It needs to be something that's highly conductive. So if you have a gold strip, go ahead. But I don't think teachers have high enough paychecks for that.
and the ball you're using is metal? It's iron?
No. The ball has to be completely insulating, so it has to be plastic.
Plastic. Okay. Okay. Thank you.
That is the ball. The ball itself, yes, that has to be light. So we're using a ping pong ball, and then we color it with conducting paint.
Okay.
Yeah.
Thank you.
Gladly.
Yeah, and if you did not know what experiment it was, we will post it. You can find the video on our social media, and Anya maybe can add a comment there to showcase what it was and add the instructions that you just shared. Thank you, Anya. And I think it would be great to end this discussion session with a bonus experiment that Mark has prepared for us. And we have a... which hopefully he knows what it is. Just to have some fun at the end. We have no game. It has a lot of names, right? It's shells. And this time with plastic cups.
So yeah, we have some plastic cups. And I have a camera. Okay, I will just put it more down. So
yeah.
Okay, so we have here 3 cups, and most of the time when you go on holiday in another country, you walk down the street and you have some people who will say, come, we have an experiment and you can earn money. So they call it balletje in Dutch. I don't know how to call it in English. And yeah, it's a ball. In the center, the cup goes down, and then they will do this, and then you have to try to guess where the ball is. So in my classroom, in our classroom, we do this a little bit different. We do this with water. So we have some water, we pour it in a cup. So, and then I ask my students okay, look closely, because I will ask you in which one of the cups the water is. So I will try to do this as great as possible. And hopefully you will look closely. So, in which cup is the water? Is it?
Okay, so
it's in. Is it
okay, so let's ask David. Where do you think the water is?
Oh,
Sarina's
right.
left, or right?
Right.
Sarina's right.
Sarina's left.
Sarina's left.
Yeah,
Sarina's
my
left.
left and your right. Okay. Okay, let's see if it's
Adam?
correct.
Yeah, I think the same.
Okay, we all think the same.
Yeah, okay. So you were correct. You had good eyes. So we do it again and keep a close watch. So in which one is the water now?
I'll now ask Anya. Anya, did you follow? Where do you think the water is? Okay, we did not hear you, so I ask Adam. Adam, where do you think?
I think it is on right next to the right hand, like
Sarina's right.
Sarina's right hand. Yeah, that one. That one.
David, do you
Okay.
agree?
Yep.
I think that we have an agreement. This should be there.
There's another look. Okay. You do it.
Yeah, we're pretty good at this,
Okay,
right?
okay. Just one more time, okay? One more time, and I promise it will go.
Right.
Hopefully, again, you will have the right cup. So, in which one is the water now?
I think we're pretty confident now, right? So,
Yeah.
what do you think?
Center.
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 The
Center.
Absolutely
Yeah.
center.
I will be victim. Come on.
Yeah, okay, Mark. And so you guys are sure it isn't this one, right?
Yep, pretty sure.
Okay, so I can put it here and
Yeah, it looks suspicious, so sorry, Mark. But yeah, no, it's it. Okay, okay, great. Perfect.
so, good job, guys. So a little bit behind so they can see it better. Okay, so it also isn't in this one, right?
Yeah.
Okay.
Correct?
Fingers crossed. Okay, you were right. A little bit,
Umbrella?
yeah, umbrella and a little bit.
Okay.
Okay, are we going through with this?
Should be in this one, right?
Yeah.
Yeah, and do we want to see Mark wet?
Yeah, you are.
Yeah, we do.
Okay,
Okay.
let's try this.
Sorry, Mark. And nothing.
No, it isn't in this one.
Where is it?
It also isn't in this one. And it also isn't in this one. So, where is the water? That's
Where's
the
the water?
question for you
In the
guys.
center one. In the center one.
Yeah, it's still there.
Depends on the answer.
No water here.
Yeah, the guys here have a theory they're still there. But yeah, I don't know. Maybe we can leave it to our audience. And maybe we can cut it here and show it later on our social media what happens. Can we do that?
Yeah, that's okay. Yeah,
Perfect.
of course.
And this was a perfect advertisement for our next stream, which I already said was tricks. And so if you want to see more of that, I invite you to join us 12th of December, just before Christmas, 7 p.m. as usual. And at this point, I would like to thank our dear guests. Thank you, Mark. Thank you, Sarina. Thank you, Anya. Thank you, David. And thank you, Adam. And also to our team here that makes this happen. There's a team of 5 people here in the backstage making this stream possible. And even through all the difficulties that we had, we pushed through. I think we had a great night. I hope that all of you did as well. Had a lot of fun. And I will be looking forward to see you again in 6 months. Until then, have a great rest of the day. Have a great holiday season and a new year and whatever happens until then. Good night. Goodbye.
Bye-bye.
Bye.